ICGT. We will start a more theory-oriented session with a talk by Richard, aka Richard Eggert from Duisburg-Essen. That's all. All right, thank you very much. So I'm Richard Eggert, and I'll be presenting joint work with Paolo, Baldan, König, Timo, and Tommaso, Padoan, and also greetings from Barbara. She sadly couldn't make it, but I'm sure she would have liked to. And okay, this paper is called the Monoidal view on fixed-point checks, and basically this paper can be seen as an extension to a previous paper, Fixpoint theory upside down. And we put the framework or the theory of this paper into a categorical setting. And in fact, we obtain a symmetric monoidal categories. And this allows us to obtain function decompositions and their approximations as graphs in some sense. And also, we created a tool from these fixed point checks. But okay, this doesn't make a lot of sense to you because you don't know what's happening in this paper. So we start with a short review of the paper, fixed point theory upside down. So I guess get paper one talk. Okay, so we start the review. So given some monotone function of a complete lattice, we know that this function has least and the greatest fixed point. And the challenge we tried to tackle was, given any fixed point of this function f, and somehow identify if it is in fact the least fixed point or the greatest fixed point. Okay? And I'll be introducing a really simple example. So to illustrate what I'm doing, we use Markov chains, pretty standard, I would say. We have a finite state space, a subset of terminal states, and each non-terminal state transitions via some probability list. Right? And we are basically interested, okay, given such a Markov chain, and I start at any state, what is the probability that I will eventually reach some terminal state, any terminal state? And okay, we can compute this termination probability as least fixed point and the least fixed point of the following function t. And what does this function do? Well, if S is a terminal state, then it assigns termination probability 1. Right, makes sense. Otherwise, it sums over the probability of going to the successor times the probability distribution, termination probability of the successor. Okay? And if you have the least fixed point of this function, then you know the termination probability of each state. Okay? So let's say we have this simple example, right? And the termination probability of each state is given by these values in green. Pretty simple to see, I would say, because I mean, U is a terminal state, so termination probability is obviously 1. These two states, they just run in a cycle, so they can never reach this only terminal state U. So termination probability is 0. And lastly, the state X, I mean, at some point it either goes here or there, and termination probability is 1. Okay. But now, so this is the least fixed point of this function t, but it also has different fixed points. For example, each state, this termination probability 1, is also a fixed point of this function. Okay? And we can kind of see what's going wrong here, because state Z is like, my only successor is state Y, right? And he terminates with probability 1, so I terminate with probability 1. That's the same holds for state Y, because he thinks, my only successor is Z, he terminates with probability 1, so I terminate with probability 1. Okay? So these two guys, they basically convince each other incorrectly that they terminate with probability 1. Makes much sense. And this is what we call the vicious cycle. Okay? And basically the task now is to find these vicious cycles in the system. And if there exists one, then this cannot be. All right? So, to be a bit more theoretical, I mean, we can't just work with monotone functions over complete lattices. Our theory works for functions of the following kind. So functions from M to Y to M to Y. So this is a set of functions mapping from Y to M. And Y is some finite set. M is a complete MV chain. I mean, these MV chains, there's some algebraic structure. But for this talk, it's Right? You just think of them as the zero one interval, this truncated addition and subtraction. Okay, and additionally, this function has to be non-expensive. Basically, you take two elements and you apply f, and the distance doesn't increase. All right? So, I mean, it's somewhat more restrictive, but as we will see, these additional properties actually prove quite useful. But okay, let's talk about how can we find these vicious cycles. So, given some fixed point A, how can we find out if it's the greatest fixed point? I'll be jumping around a bit with greatest and least fixed point. But okay, here it's for the greatest fixed point, right? And for this, we use a Galois connection, and we connect this set of functions from y to m to the power set of y. Okay, and this function alpha, it takes some subset, and it adds to a the value of delta at certain points. Okay, and this function gamma, it takes some mapping from y to m, and it checks for each element. Here's the value of b, delta above the value of a. Right? This might be somewhat confusing, but here are some nice pictures, and you will probably understand better. So this is a, right? It maps these elements to these values, and this is the value delta. Okay, and then let's apply alpha to the subset y1, y3, and y4. What's happening when we just increase these three values by delta? Okay, and then let's say we have some different function b, which has these values in b, and we apply gamma to it. And only thing we do is we check, okay, is the value of b delta above the value of a? And this is exactly the case for these three guys. Right? Okay, and with this, we can define this approximation function, which will detect these vicious cycles. And this function is just defined as first you do alpha, then f, and then gamma. Okay. And now the question is, how does this function find these vicious cycles, right? So let's say you have some fixed point of this function. Okay, well, what does this mean? First, you apply alpha, right? So you increase these values by, okay? Then you apply f, and you land, let's say, here. Okay, you obtain these values too. And then you apply gamma, and you obtain the same set as before. But what does it mean? Well, you increase these values, then you apply f, but everything you increased stayed up there, right? So this, in fact, means that a plus delta y prime is the post-fixed point of f, right? And post-fixed points are always below the greatest fixed point, and it's above a, so a cannot be the greatest fixed point. Okay, right? So basically, you want to find these fixed points, and if there's none of the empty sets, only fixed points, you know there's no vicious cycle. Now, to dualize the theory, we ask the same question: is A the least fixed point of F? And the slide is a bit more technical because I need this later on. But in the end, you do pretty much the same thing. You reduce values, then you apply F, and then you check, okay, was this decrease kept? Okay. But we can define these hash functions, or I would call them approximations, for functions which are not end functions, and we will see that this will be quite useful. So let's say you have some function f from m to y to m to z. Then we can define this approximation as follows. Doesn't matter too much what's inside there. I mean, it's probably very hard to pass. The end of end function, like I said, you do the same thing, reduce, apply f, check if decrease was kept. Right? But I should also mention I was not super complete before, right? So we actually don't use the power set of y, but we restrict to the power set to this function power set of the set ya. And the set contains all elements with a value greater than 0. And this makes sense, I mean, because if you're at 0, then you don't have potential to go lower. Right? So the state cannot be efficient. Okay. Right. So We had the following main result, given some f, which is a non-expansive function, and some fixed point of this function. Then it holds that a is the least fixed point if and only if the greatest fixed point is approximation is exactly the same. So basically, the function doesn't have vicious side. All right, and for this example we had before, we can also see that this is a fixed point of this function. So in fact, it's a vicious cycle. I mean, I don't really want to go into too much detail what's down here. I mean, you probably believe me that it's a vicious cycle, I would say. Okay, now let's go back to why it's quite useful that these functions are non-expensive. Because non-expensive functions enjoy really nice Closure properties. So they're closed under composition and closed under disjoint union. And this allows us to assemble more complicated functions just from a basic function. And what's additionally nice, we also obtain the corresponding approximation from this basic function. Okay. So, I mean, like I said before, it's quite useful to define these approximations of functions which are not any function, and then right in your decomposition you could have a function. Okay, so for example, this function t we had before, we can decompose it as follows. So into these three basic functions. First of all, we have this constant function c, and all it does is it assigns the value of 1 to our terminal state. Okay. Then second, we have this average function, which basically assigns an average sum to each probability distribution. Okay, and then lastly, we have this function eta. I'll call this an reindexing function, and it chooses the corresponding probability distribution for each state. Okay, and then we can use this disjoint union, and we obtain this function t from these three basic functions. Okay, right, and we can also draw like a nice string like this. Okay, so this is like first part of Fixpoint theory upside down, and now we go to the original paper now. So we put this approximation framework into a categorical center, right? And we have these two categories, the concrete category C and this abstract category A. Okay, and in this concrete category, objects are those mappings from Y to M, and arrows between two objects are exactly these non-expensive functions such that f of A is. Okay, so these are basically the functions we want to analyze or search for vicious cycles. And the approximations, they live in this category A. Objects are the same. I mean, I could write YA for A for these objects, but there's the same information, so it's a good point. And arrows are monotone functions from the power set of Y to power set of ZB. Okay, and then lastly, we have this functor connecting these two categories, and it maps an object to itself. Okay, and now, interestingly, it maps a function to its corresponding approximation. Okay, so these are well-defined categories, and this is a functor, and we can actually enlarge these categories to become geomonoidal categories. These are basically special symmetrical monoidal categories, and we additionally have a duplicated this charger. Super important, I would say, especially for this talk. But okay, we have additional operators like this tensor, which somewhat serves as a disjoint union and neutral element symmetries, and like I said, this charger duplicate. Okay, and I mean, as we also kind of seen in the first talk of today, these symmetrical categories, they fulfill certain axioms. I want to go over them in detail, and we have some additional, right, for this duplicator and this charger as well. But okay, what's most importantly is that this function, as this functor hash, is also geomonoidal. right? And this says, okay, it is compositional, and we can obtain the approximations. It's basic functions by assembling these basic functions. Okay, so that's quite nice, right? So you have a super complicated function, you can like dissect it and compute the approximations for each part and then stick them together. And you get the approximation for this complicated function. Okay, and now based on this, we derive the tool which basically does these Fixpoint checks, right? So you have a function A, yes, mapping A, and it's a Fixpoint of this function. Then this tool tells you, okay, this is in fact the Fixpoint of this Fixpoint dual. And okay, in this tool, the user can compose his very own function via some basic function templates. And well, building such a function requires 3 steps. First of all, you need to know what is the NV algebra. Okay, but we keep it simple here. It's just the 0, 1, and 2. Then the second step is, okay, you need to specify your basic functions. Right? I mean, it's not enough to say, okay, I have here a constant function. You kind of need to, okay, what is this constant function? What constant am I mapping to? And lastly, we assemble F from these basic functions. Okay, so this is how the tool looks like. It's probably kind of hard to see, I'm sure. But okay, basically you have these basic functions here on the right, and you can drag and drop them in this middle area, and this will create a basic function box. And then you can just compose them, use this joint union. Okay, and for example, this is like this termination probability function we had before, right? We have constants and reindexings and average. And these are the parameters you need to specify in the tool on this left-hand side. And lastly, we have this testing box, and this is basically where the magic happens. And I will talk about this later on. But okay. We should also talk about how do we specify these basic functions. Okay, so in the example we had before, we had 3 basic functions: this constant, this average or expectation, and this reindexing function. And the constant function in general looks like this, mapping from 0, 1 to y to 0, 1 to z, and it maps some a to a constant k. Good. So to specify this basic function, you only need to know, okay, what is this input zy, output zz, and the constant you're mapping to. Okay. Then for the average function, you even need less parameters. You only need to know, okay, what is the set, and what I mean the set of probability distribution. You automatically get it from y. To be fair, I should say, restrict to a finite subset of this power set, which is not a problem. But okay, you don't need anymore any other additional parameters. And lastly, for this reindexing function, right, this reindexing can be written as follows. And you need to know what is this input set, this output set, and I mean, what is this reindexing? So going back to our example, right, you might remember this constant function input set was just an empty set, output set was just this only terminals and u, and this k, okay, it maps u to 1. Okay, for the average function, y is just s, z is the set of probability distribution over s. And lastly, this reindexing function, right, you have this reindexing which selects the corresponding probability distribution by which each states transitions. Okay, and now the task is, okay, to put these things into the tool, then you specify these basic functions and you compose them and you obtain the function you want. So these contents you need to specify, and it's probably not bad to see, but it's probably good enough. But for example, the set S without T, you just input these 3 states. But you can have other types of sets, for example, the set D of probability distributions. Like I touched on, you restrict to a finite subset. And you only need 3 probability distributions in our example, right? Because I mean, this reindexing function, right? X transitions via probability distribution P3 and so on and so on. Okay. And lastly, I mean, you also need some fixed point. You want to check for being the least fixed point, right? So you can input such a mapping which maps each state to the value of one. Like the fixed point we had before, we have this vicious cycle, right? Okay, so now this testing box at the right hand side, this is basically where the magic happens. And there you can input A, some fixed point A, right? And then the tool checks, okay, is this indeed a fixed point? And if it is, it computes the greatest fixed point of our approximation, right? And that would then be, then you know, okay, there's a vicious cycle. A is indeed the greatest fixed, the least fixed point. But otherwise, you know, okay, there's a vicious cycle. And then you can go on. So let's say we input this fixed point here, and the tool tells you, okay, this in fact is a fixed point, right? And it also finds the vicious cycle, right? States finds that we're in a vicious cycle. But tells you, okay, there's a vicious cycle. This is not the least fixed point. It is in fact the greatest fixed point. I mean, makes sense, everything is at one. Can go higher. Okay, now to talk a bit more what this tool can do. But it can check if some fixed point is the greatest fixed point. And if it is not the least fixed point, right, then you can find a prefixed point below A, but still above the least fixed point. Right. This is somewhat important for algorithms. For example, we had a generalization of strategy iteration where this results came quite handy. And also, if you have a post-fixed point A, you can check, okay, is this post-fixed point below this fixed point? Sadly, it's an incomplete proof rule. So sometimes says, okay, this is indeed below the least fixed point, but sometimes kind of doesn't. I mean, it doesn't tell you anything wrong, you just get back the conclusion. All right, so what we've done, we enriched the theory from our previous paper, and we built the tool for this theory. And what I didn't touch on at all, basically, but in our paper, we were also able to embed general predicate liftings into our approximation framework. So basically, we have this hash function for general predicate lifting. Okay, to name a few applications like two-player games, simple chassis games, or energy games, for example, or behavioral metrics for state-based systems, Hilbert Markov chains, metric transition systems, probabilistic automata, example, and other basic functions that are also in the tool, constant indexing we've seen. We also have a maximum and minimum addition subtraction, and the other average. Okay. So, future work, I mean, the tool is or you can enhance the use somewhat. And also, I mean, this approximation theory is quite interesting. And like I said, based on this, we were able to derive a generalization of strategy iteration. And probably, or maybe there are other applications. I'm pretty sure there are other applications, maybe also some other scenarios where this theory can come in handy. Okay, that's it from my side. Thanks for your attention. So, we have any questions? Wondering what is the typical agent scenario for this? For the users, because you mentioned usability and what are the kind of challenges in terms of the size of the problems that you address if you want to use that in those, whatever the kind of application areas are. Yeah, you mean for the tool or for the general theory? Okay, I mean, if there's a tool is a bit more for playing around the proof of concept. Yes, basically, I mean, you can input some larger systems, it works, but it's kind of a hassle. Like I said, the use of the tool is so great. But I mean, it works. But yeah, probably you have like a super big system, might be kind of rough. Like this.
How big would the typical systems be? Or is that difficult to say because you're not targeting a particular application domain?
Yeah, when we developed the tool, we were more like, okay, can we insert all these examples? Basically, this was more the question we had. Okay, and this works. We put some easy example for all of these. We didn't really do a lot of texting or topic.
Was there any picture actually the graph transformation? It's like I can find the point.
Graph transformation, not too much. I mean, you have these symmetrical monoidal categories, right? So like this.
So that's big diagram.
Yeah. There's not too much transformation, I would say.
All right. But then I have what would it be to transform these things? I mean, when you have a model, so to transform the model, what would that be? Would that be a refinement? Would it make sense to study emotional refinement, where it says to place some section of this by a box representing some kind of abstraction, or the other way around, or refinement, sort of taking the box and representing it by a, I mean, that's what Richard for lunch had this like the notion of point graph, where the graph represented some kind of physical or engineering system, and he used rules to describe refinements of those. And they have got input and output, energy, reads, and things like that. I mean, it's so at some level, I guess, conceptually not very different from a representation. I mean, the details are different, but you could think of it as a similar graphical representation of something that describes some kind of flow in a way. Mm-hmm. Is there a notion of abstraction on these, or refinement, or refactoring, or I mean, that's what you would normally have to transform models, right?
I mean, basically, this is a function key, right? Just decomposed in some way. I mean, I guess it's some sort of refinement in that sense, but yeah, I'm not really sure.
Would that exist in that domain? I mean, that's the question. Is that an interesting concept in that domain? I don't know enough about the domain.
Yeah. I mean, me probably neither, so I'm not.
Many modeling languages or modeling formalisms basically have notions of refinement and something. Okay.
Yeah,
I see the speculation.
Yeah, sorry, I'm not too sure.
Right, so it's nice to see that.
Exactly. Yeah.
Was natürlich so. It's yeah, it's okay. And then how it's going to do this. Perfect. So my name is Aloïs, and I will join work with Vrije, which is there, and my supervisor Jörg. And the title of the paper is Fuzzy Presheaves by Quasitoposes. So let me try something for this presentation. I will, since it's a theory presentation, I will try to give you the meat of what this paper is about, so that you know like what to retain from it, and maybe know like what to look for in the presentation that the part that interests you. So the contribution of the paper is summarized as like we've looked at a class of categories, namely fuzzy Presheaves, which is a notion that we introduced, are all RM additive Quasitoposes. And why is that useful to know that you are an RM additive Quasitopose? It's for many reasons. For instance, there is a PBPO plus termination technique with Aloïs that he will present in exactly 2 hours here. That needs the category to be an RM additive Quasitopose. Also, the formalisms typical as that he defined subsumes order when you are in a setting of a Quasitopose. And also, Quasitoposes have been proposed as a natural setting for nonlinear rewriting. And now, why do we care about fuzzy Presheaves? Because fuzzy Presheaves offer a practical treatment of graph relabeling, and I will illustrate that in a slide later. So this is the takeaway from the presentation, if you want. So in the title, there is fuzzy Presheaves, as I will define it later. First, Presheaves, just a quick recall, if not everybody might know what it is. So a Presheave on the category I is a functor from I up to set. So what that means is that for every object in I up, you have a set, and every arrow in I up, which I call like identity iota, you have a function. And the identities and composition must be preserved. And a Presheave morphism is simply natural transformation between the functors. So a function for every object in I, every object I in I up, and a naturality squared and musculus. And this gives you a category called the category of Presheaves. And why is that useful? I really like this definition of Presheave because it's visual. And the category I up gives you a template of what the Presheave will give. So if you take the category I up to be just one object, Presheave is a set, and Presheave morphism is just a function. So you retrieve the category of sets. Now, if you take 2 objects in the category I up, you have a Presheave with just 2 sets, you obtain the category set squared or set times set. If you add an arrow, you overlap between them, you obtain the arrow category. Now, if you add another arrow, this is probably the example that all of you know. If you have 2, you have a Presheave is like an edge set, a vertex set, and a source and target function. So you retrieve the category of graphs. What's interesting when we can extend on that famous example of how we can see graph as a Presheave, like we can add like a 3rd arrow, where this time like an edge, there's still edge set and vertex set, but this time an edge has like 3 components, like a first source, a second source, and a third source. So the category that we obtain is the 3 uniform hypergraphs. You could add as many arrows as you want, and you can have hyper edges of the size that you want, giving k uniform hypergraphs. And you can combine the last 2 examples to obtain like where you have like 1 set for every integers that you want starting from 2. You could also start from 1 if you want hyper edges of size 1. And this gives you hyper edge of every size that you want, so the category of just hypergraphs. And with this notion of hypergraphs, note that the homomorphisms preserves sizes of hyperedge. Whereas there is another possibility for hypergraphs where you can define it on the walking. If I up is the walking span, then you obtain another notion of hypergraphs where you allow multiple instances, and where the notion of homomorphisms don't require sizes of hyperedge to be preserved. And until now, like we've seen, like ordered edges. If you want to have unordered, if you want undirected, you can do that by changing the category up. So you can define composition, and if you add like an symmetry arrow here, with those equations, you obtain indirect graphs. And another possibility is if you had like a reflexive arrow here in I up, you obtain what is like called reflexive graphs or degenerative graphs sometimes. So that's the reason why I can really like Presheaves, is because by defining a graph, like a category where you have composition identities, you can obtain many categories of graphs in one go. And the beauty of that is also in that result that every Presheave category is a topos, and topos is a very strong construction because topos are also graphs, topos also additive, etc. So being a topos is neat, and you have all that in one go. So this is like the setup where we've seen like with the beauty of Presheaves. Now let's talk about the second part of the title, like of fuzzy Presheaves, like fuzziness. Fuzziness, I guess just a quick recall. What is a fuzz set? It's a set where it's no longer, the membership is no longer binary. It's no longer in the set or out of the set. They have a range of membership from 0% to 100%, right? And the corresponding notion of morphism for fuzzy sets is just a function that does not decrease membership. And visually, a set is represented as a Venn diagram, and a fuzzy set you just blur the border, right? That's hence the name fuzzy. While the closer you are to the center, the bigger the membership, and to the outside, the less the membership. You take as a convention that you have membership 0, you are not in the fuzzy set. And if you want to have more general definition than just having the unit interval as your range of membership, you can take any poset of your liking. But for the presentation, for the slides, I will usually have like membership in the unit interval and written like in superscript, like this, for easy reading. So this is the notion of fuzzy set. You can easily have also a notion of fuzzy graph where you just have membership values on both vertices and edges. And the notion of morphism just asks for both functions of a graph morphism to not decrease membership, generalizing the notion of fuzzy sets. So for instance, if this is a graph, just put a membership on anything, and this is a fuzzy graph. And for some authors, what I've done here is like illegal. Like here I have an edge with membership 80%, and it has the source with membership 50%. For some authors, there is this requirement that the membership of an edge must be smaller than the membership of its source and of its target, which makes sense if you talk about membership, because for instance, if an edge is fully in the graph with membership 100%, it makes sense that the source and target must be 100% in the graph. So why do we care about fuzzy structure? What our goal with it is. It's interesting because if you see the membership as a label, so forget that it's a membership, just take it as a label, but now the labeling set has a structure, poset structure. And when you ask for that poset structure to be a lattice, a complete lattice, so you have join, meet, bottom, top, then the formalism TBPO plus gives a practical treatment of graph labeling, where, for instance, if you have an edge and the source has like label X, membership X, but now we see it as a label. If you want to change it from X to Y, you can do that in just a single TBPO plus rule. Whereas, for instance, if you wanted to change the membership on the edge, this is something that you could do in TPO, for instance, but then it would not really be called relabeling, it would more be called replacement, because you could delete the edge and create a new one with the label anyway. But doing that, where you change the label, whatever the context and without touching the context, this is not possible in TPO, but it's possible in TPO plus, thanks to this feature of having join, meet, and bottom. So this is the motivation. And generalizing fuzzy set and fuzzy graph, we define the notion of fuzzy presheaf. So if you take a category I and a functor that gives a poset for every I, every object in I, fuzzy presheaf is a presheaf endowed with the lax natural transformation. What does it mean in practice? It means that for every I, you have like this membership set of labeling set Li, and for every I, you also have like the membership function. So on every level of the I, we have a membership function or labeling function. And what it means to be lax? It means that this naturality square, instead of commuting, it must commute up to 2 morphism in poset, which just means like less or equal commute. So if this is a function, it must be smaller than this one. And the notion of morphism is as before, like on every level, it must not decrease. So in practice, what it means that if you take I up to just be I, before we had set, now you have fuzzy sets. If you take this one, before we had graphs, now we have fuzzy graph. If we take both sets like LE and LV to be equal, and if we take this poset morphism L iota to be the identity. So in fact, this definition of fuzzy presheaf is more general because you can put the constraint that you want between the levels. So if you want to obtain the notion of fuzzy graph, as before, you just take the identity here. But you could ask any other constraint. Like you could add the constraint that the membership of the edge is smaller by a factor of a function that you want, for instance, of the source packet. So you could do more stuff if you want. And you could keep going. Like if you take that before you had 3 uniform hypergraphs, now you have fuzzy 3 uniform hypergraphs, and you could keep going. And what is known about fuzzy sets is that when L is a complete Heiting algebra, then, which is the case, for instance, for any Boolean algebra or for the unit interval 0, 1. But you have a Quasitopose, And what we extended to is that now when you have like every level being a complete Heyting algebra is still hold, like we still have Quasitoposes, but also that we have our additivity. So now the rest of the slides will be like giving a high level idea of the proof of like what's the interesting concepts behind those proofs are for those that are interested. And yeah, we start first by the Quasitoposes part. So to be a Quasitopose means that you need like a few things to be satisfied. You need finite limits, finite colimits. You need regular subobject classifier and no Categorical close. So I will try to give like a idea of what those concepts means for those of you that don't know. First, I will just prove two limits, like give the idea of two limits, and start with the terminal object. So it's an object that has a unique, that every other object has a unique arrow into it. And for sets, it's a singleton set. For graph, it's one vertex and one loop. For Presheaves, you just generalize both cases as such. And for fuzzy set, you take the terminal object of set and you give full membership to its element. Similarly, for fuzzy graph, you take the one from graph and you give like full membership to every element. So with no surprise, this is the terminal object for fuzzy Presheaves. You take the one from Presheaves and you give full membership to every object. Similarly, the product, which is like an object created from two and has two prediction and universal property. In set, it's the Cartesian product. In graph, it's called the tensor product, with the definition as such, like in the details of it. Or visually, you could like, this is the image that you find on Wikipedia if you look. The product of those two graphs is this one. And generalizing to both of them, you have the product for all Presheaves. Now, if you look at fuzzy sets, the way to define the product between two fuzzy sets is the product in sets. And you just have to take like a function, specify the function and on the product, which is just the meat of the memberships. So similarly as for the terminal object, the way to have products for fuzzy Presheaves is just to combine the examples above and voila, you have it. This is the idea for like the limits and colimits. The rest of the limits and colimits are similar. And as you can see, just combine what you already know and it works. Another thing that you need to be a Quasitopose is to have a subobject classifier. So informally, the definition is like there is a pullback where, but visually it's like this: that you have a bijection between subobject and characteristic function. And I really like this definition because I feel like it's quite needed, quite visual, also in the graph example. But for sets, we all know that there is a bijection between like subset of a main set B, and every subset A corresponds to a function from B to the set 0, 1, where if you are like in the subset, you are set to 1 and with 0 otherwise. And now, if you ask the question, can you also do this thing in graphs? Yes, you can. And if you take, for instance, that graph B and this subgraph A, this is in correspondence, one-on-one correspondence with characteristic function from B to this graph omega. And we like this graph omega because visually it tells you everything that can be, that the subgraph can be. So for vertices, there is two options, 0 and 1, where 0 means the vertex. If you are sent to 0, it means the vertex is not in the subgraph, and if you are sent to 1, it means you are in the subgraph. And then for edges, there is like multiple cases, right? If your source and target are not in the subgraph, you cannot be in the subgraph. If your source is in the subgraph, but the target not, you are sent to S, vice versa to T for the target. And now if an edge has a source and target in the subgraph, there is two options. Either the edge itself is in the subgraph, which is in 1, or the edge itself is not, sent to ST. So we like it. And you can generalize both examples and obtain a classifier for all Presheaves. Now, if you go to fuzzy sets, there is no omega that classifies all fuzzy subsets. This is because of the nature of fuzzy subsets. But what you can do, the most that you can do is to classify all regular fuzzy subsets. Where regular fuzzy subset means such that if you take, for instance, just an example to illustrate, if you take the fuzzy set with A membership 40% and B 60%, and A as a subset with membership X, it's regular if and only if X is equal to 40%. So you need to be called a regular fuzzy subset, you need to have the same membership as the main fuzzy set. And if you take omega to be this, so the classifier for sets, and you give a full membership to everything, you obtain a regular subject classifier for fuzzy sets. So again, this is like a list of 4 examples, and you just combine them and you obtain with the idea, you combine the IDs. And if you take the classifier for Presheaves and just give full membership to everything, you obtain a regular subject classifier for fuzzy Presheaves. And the last thing to have is locally Cartesian closedness. And again, I'll just give a partial part of the definition, but not for this one. So to be first, like a smaller version of the definition is to be just Cartesian closed, which means that you have exponential objects for every a and b. You have like b to the a, and you need to have like currying, or in categorical terms, an adjunction between functions of this form and functions of this form. And again, if you look, you can do that in sets, it's a set of all functions. You can do that in graphs with those definitions. You can do that for Presheaves. You can do that for fuzzy sets with this like nice equation that tells you what happens on the membership. So combining those examples, you can find exponential objects in fuzzy Presheaves. And now this is the proof that it's Cartesian closed. Now, how do you prove that it's locally Cartesian closed? Locally Cartesian closed means you don't have only exponential objects, but you have exponential objects on all slacks categories. And I don't know if you remember it, but this the proof for Presheaves is very neat. It uses the fact that Cartesian closeness is a property that is stable under equivalence, and that if you do slice a Presheave, you just obtain another Presheave. So since you know that the other Presheave is Cartesian closed, you've proved that the slice is Cartesian closed. For that, you just need to change the category of the Presheave from I to an element category, the category of elements, if you know what that means. And so this is like well known, since in that textbook. And what we did was like generalize it to now fuzzy Presheave, where you just need to again change the I for the category of elements, but also change the functor slightly, and you still have an equivalence. So this proves that you have locally Cartesian closed. This is the idea for Quasitoposes. Now I will give quickly the idea of how we prove RM additivity. I won't recall the definition, but it's most of you probably know it, but it's like having some square property, which is the most event camper, all stable for the last one. So there's those 3 notions of additivity, like 2 beginning from the first definition. And this is like the status of what you have in general. So every topos is additive and every Quasitoposes is RM quasi-additive, so the 3rd version. And what we wanted was to obtain this middle criterion. So for that, there is thankfully a nice criterion in the literature from Johnstone that tells you when you are in a Quasitoposes, you just need to have like closed, some property on unions, and if it's satisfied, you are RM additive. So this is the property that we used to prove it. So that's it for the proof of the main theorem of the paper. Of course, when we did that, then there was like one last question that we asked ourselves. So we've proved that all fuzzy Presheaves are RM additive Quasitoposes. But if you've been careful, in the examples that I gave, there was one that was missing, one big one, which was simple graphs. Simple graph is not a Presheave, so it's not containing the results that we have. So what to do with simple graphs? Thankfully, in the literature, we know that simple graph is still a Quasitoposes, both directed and undirected. And so we extended on that to obtain the same for fuzzy simple graphs. How such? The proof for simple graph is the notion of topology on topos and of separated elements, with this result from Johnstone that if you are in topos and you take all the separated element for the topology, this gives you a subcategory, and that subcategory is a Quasitoposes. So this is a nice property that exists in literature, and for graphs, it's really stunning that if you like, this allows you to go from graphs to simple graphs. So I will give like a sketch of the idea behind it, but the details will take too much space. But roughly, there is one special topology which is really cool, which is the double negation topology that does the following: where if you have a subgraph, like the same example as before for the subgraph classifier, but if you have a subgraph and you do the double negation of it, you just add all possible edges that you could have been missing. So for that, get like that red edge. The source and target were in the subgraph, so now the double negation adds it. And because of that behavior of the double negation, when you start with graphs and you go to the separated element, you obtain simple graphs. And we extend that where we started from fuzzy graphs. And if you take the separated element, you obtain simple fuzzy graphs. There is a slight subtlety where graph is a topos and fuzzy graph is a quasitopos, so we just needed to change a bit like the notion of topology behind it, but the result still works. So this is a summary of what we did. In the same way that Presheaves generalize a lot of categories, fuzzy Presheaves that we introduced generalize a lot of stuff. We prove that all of them are RMLs of quasitoposes, given that we have complete hiding algebras. We prove also that simple fuzzy graph form a quasitopos. And for future work, we could dream of proving more categories to be quasitoposes, because this is like something that is quite difficult to know. Like if you have a category at hand and you like it and you want to know the properties, proving that it's quasitopos is sometimes really difficult. And having general like theorems or general tools to do that is always nice and handy. For that, now we just prove for fuzzy Presheaves, but we could ask like, what about fuzzy categories? Sadly, there is no consensus of what the fuzzy category is. Like if you look in the literature, there's multiple attempts to defining it, but it's no consensus. So if one day there's a consensus, we could dream of proving that fuzzy quasitoposes are also quasitoposes. Or another line of work that I've been following since this article is to try to study more this last thing about topologies to obtain more quasitoposes to see like if there's stuff to be discovered. That's it for my presentation, and thank you for your attention.
So many thanks. Yeah. So give an example, so for fuzzy graphs, where you have the I as identity. So you kind of, for example, like you have the end of that one, yeah. So what happens if it's not the identity? So what kind of fuzzy graph you get in that case? It's fuzzy graph at all.
You obtain a different notion of fuzzy graph where the constraint between the membership of the edge and the membership of the source target is as what you want. You just need to have like here a poset morphism. L of iota must be a poset morphism. And for that, and a poset morphism is just a monotone function. So if you take the identity, it works, but you could also have something like a projection that raised the membership up to whatever value you want, for instance.
You could say membership of the nodes need to be twice the membership of the edges, something like that.
Yes, if you have like a setting where like taking the double is a monotone function. So from 0 to 1, you would have like maybe take the double until like half, and for half everything to 1. Yeah. So for instance, if I'm not mistaken, that's indeed a monotone function, you can need like just add like factor 2 in front of the condition for the edge and some target function membership. Yeah. And if you want to don't want that relationship, that constraint between the memberships of label and edges, you can also remove that part of the definition and the results still hold. Or another way to do it is, for instance, to send everything to top, because having like everything to bottom, I guess, because the bottom is smaller than anything. But you could also just remove that constraint and the results still hold if you don't want that. And at first, we didn't want to have that constraint because for the reason that we want, which is like a pre-labeling, this is not needed, because having this constraint just reduce the number of what you can call a fuzzy graph. So it doesn't change the application that we're actually doing. Just restrict if you're lucky. Yeah, other questions?
Yes. So you mentioned very briefly that apparently these fuzzy sets are quite well known, and then for fuzzy graphs, it seems any other applications for these fuzzy graphs you have in mind? Or I mean, you seem to have a very particular rhythmic application, but did you in your research find any uses for these fuzzy graphs, maybe outside of mathematics?
So yeah, except seeing, so I don't know the normal use of fuzzy graphs with the membership. I just know the one where you see the membership at like any label that you want. I guess like maybe like fuzzy set is like, well, fuzziness is used sometimes like in in AI or neural networks. So I guess maybe the notion of the neural networks where they have strength of connection is represented by membership. Maybe it's some kind of fuzzy graph that they use.
Well, I mean, that was my question, because it seems like now it's technically one of the obvious applications seems to be that graph transformation using the particle structure would ability to change weights in neural networks.
Yeah, exactly.
It's will have I don't know if that's useful, but I mean, you could introduce new actions, computing effectively some sort of. I mean, that's fine. You do now these push outs and pullbacks, and then particles with the weights and your closed model or edges and have weights right. You can do the writing. That's this sort of relationships.
So I don't know how they do it in AI or how they change the weight, but they do it automatically. So I'm sure there is some technology behind.
The application of fuzzy graphs in machine learning. I mean, that's networks. I mean, essentially there should be relations to neural networks, but I'm not sure that actually sort of physically work with fuzzy graphs.
Yeah.
As a notion. But there are other forms of machine learning, I think, that were based on fuzzy graphs.
Mm-hmm. Yeah, I have a friendly engineer that told me that it's used, but yeah, I have yet to discover and study how. That's a good question, and that's a good application potential.
And you could do all the hypergraphs as well.
Yeah, you could do hypergraphs. Yep. Yeah. So this is included in all Presheaves. Yeah, which is neat.
And then the other question was, so which role is the hashing now interested by? I mean, is that a strong restriction? Patients of you. I remember reading this book about negation instead of double negation. So exactly workaround here, not having
yeah, good question. So for the fuzzy sets, if you have a complete hiding algebra, you have Quasitoposes. It's kind of natural requirement to us, because a complete hiding algebra is by definition. If you see a poset as a category, to be a Quasitopose is the same as to be a algebra. So it corresponds to it. Now, for this theorem here about stout, this is an implication, but is this an if-and-only-if? This is not known yet. I tried to look into it if it's an if-and-only-if. It's not that obvious. It looks like it should almost be the case. But for instance, already if you take bottom, the top element is guaranteed by the terminal object, but the bottom element is not guaranteed by the initial object, because the initial object is just the empty object. So already for the bottom, you have a problem. So it may be that you have an if and only if you just remove the bottom object from the complete hiding algebra. Yeah, but indeed, that's a question.
Excellent.
Thank you.
Next speaker. And kind of the session will begin by your Jörg. Derivations and derivations.
Yeah, thank you. This is on moving derivations along derivations, preserving the spine. Is it joint work with Sabine, Kuske, Aloïs, and Aljoscha Windhorst. And we have related two long-known concepts, the local Church-Rosset theorems on one hand, with respect to moving, and the restrictions of derivations to get spines. We are dealing with edge label directed graphs, morning expense as rules, and double push out as rule application. Just that you know, and you will see it later. So let me remind the local Church-Rosset theorems. You saw them already in the morning and Robert's talk. So the first one says parallel independent rule applications are confluent, as far as I remember, proved by Art and Eggert and Barry Rosen. And the second says sequentially independent rule applications can be interchanged. This was proved a bit later by Hartmut and me. It is not very difficult to see that this can be generalized to derivations. We do it in the following way. We consider a pair of sets of rules and call it parallel independent if each application of a p rule and the p bar rule to the same graph turns out to be an independent pair of parallel independent pair of rule applications. And then you can show that every p derivation and every p bar derivation applied to the same graph can be is confluent, so it can be applied one after the other with the same result. The proof, as I said, is somewhat simple. We prove it by two inductions on the derivation lengths, starting with one step horizontally, then zero vertically is trivial because the rule application does the job. Induction step is a bit more interesting. With respect to the first rule application, you apply the local Church-Rosset property, and the rest is done by induction hypothesis for the derivation of length n. The second part is for the length of the horizontal derivations. Zero case is again totally trivial. The induction step is again simple because with respect to the first rule application, horizontally I have proved it already. It is an induction before, and the rest is done by the induction on n. One way to look at this construction is that you move the horizontal derivation, the vertical derivation, say d, along the horizontal one, say d bar. So we call it moved variant and denoted by move d bar. Backward moving can be done more or less in the same way. You need sequential independence instead of parallel independence. So a pair p bar of rule sets is called parallel sequential independent if each p bar rule application followed by a p rule application. Please note the order of the applications is sequentially independent, and then you can interchange p derivations followed by p bar derivations followed by p derivations in the way like the local Church-Rosset theorem. It can be proved in the analogous way to forward moving if you replace parallel independence by sequential independence and conflux by interchange. But here is another simpler way to get it because we use Monix as rule, so they can be inverted. And this means the horizontal derivation can be inverted, and then backwards moving becomes forward moving along the inverted derivation, denoted by E1 backwards. Let's have a look at an example. The first set of rules here considered is P color. We have three types of rule. The first rule adds a loop to a vertex. The second rule adds just a vertex with an I loop. I is added color. And then you can choose a color for the A-looped vertex, and you can connect such a vertex with an I color vertex by an edge. In this case, the A loop is removed. So you can color only once. So the sample derivation on the right, you see, starts in the complete bipartite graph K33 with 3 to 3 nodes. And first, one may add A loops to each vertex, then 2 colors are added, and finally the 3 left vertices are attached, connected with the color 1, and the other 3 with the color 2. This is the 2 coloring of the K33, but this is not really important here. I use it just as a derivation. Second example is the set P-dual. P-dual, it allows to double an edge in the way that you add the B edge in parallel to a given edge. You can add an edge between 2 vertices, and if you have a parallel pair of edges, one with B label, one unlabeled, then you can remove it. And the way to apply it is, you see it in the blue box, you double all the existing edges, you add edges where no edges were before, and then you remove all the thick edges, which are the double edges. One can prove, and again, this is not very difficult, that these 2 sets of rules are parallel independent of each other, and P and P bar are also a pair of sequential independence, so you can move the left, the yellow box to the right, here the orange box, and if you look into both of these derivations, you see the restriction to the 6 vertices yields the same derivation. So the 6 vertices get loops, you add 2 colors, and then 3 vertices are connected with 1 and 3 with 2. This means in this case, the given derivation and the move variant have a common restriction, and this is obviously the minimal restriction because you need the 6 vertices. With less, nothing cannot be done what is done in the derivations. This is
okay. So this is a trace, right? You're talking about the trace. You're exactly describing the trace.
Yeah.
So how do you relate to this one? That's the minimal derivation trace in these 2 steps. That's why you need to.
Wait a second, I define it.
Okay.
So it is. It turns out that this is not at all a good incidence in this example because it is a general theory. And to define this, I need restrictions, and restrictions require excess parts. These are both concepts introduced by Hartmut and me in 1977, and the proofs, the needed proofs are in my PhD thesis. So excess part is inductively defined on the length of derivation. So the 0 derivation, obviously nothing is excess. So the empty graph is the excess part. And if you have a derivation of length n plus 1, you consider the first step and then the final, the last n steps. And the yellow box shows you that by induction hypothesis, you can assume that you have already an excess part in G1 in the first derived graph. Then without loss of generality, you can construct the first derivation step in such a way that the intermediate graph or the push-out complement is subgraph of the start graph as well as of the derived graph, so you can intersect the two. They contain all the excess items that are accessed from the second step on. But the intersection is also in Z1 and in G0. So you have these items also in the start graph. And if you want to know all the excess items, you have to add the match of the first rule by union. So we have the excess part of the derivation constructed. You need this in the following way to construct the restriction. Again, inductively. So the zero case is extremely simple. It can be restricted to everything. The interesting is the case where you do just one rule application. Then it is well known and obvious that you can restrict always to a graph that contains a match of the rule applications, because the restriction to the subgraph fulfills the matching morphism, fulfills the gluing condition. So you have a short complement and then the deriving complement on the right-hand side. By some reasoning, you can show that the following holds, that whenever the excess part of the whole derivation is in the subgraph, then the excess part of the n last steps is in the derived graph of the first step, restricted to the G1, restricted to G1 and G1 prime. And this means that by induction hypothesis, you can restrict the n last derivation steps, and clearly composed with the first step you have already restricted gives you the whole restriction. The excess part is a special case of such a subgraph G prime. So you then can restrict to the excess part, each derivation to its excess part. And it is obviously the minimal one because it has to contain the excess part. And there's nothing smaller than this. So it really is. This allows me to formulate the main theorem whenever a pair of sets of rules is parallel independent. Then the following holds. If you have two derivations, D and D bar, P derivation and P bar derivation, starting in the same graph, then the spine of the given D derivation and its moved variants are equal. I will show you a little bit how the proof works. I cannot give all the details. It follows the inductive definition of moving. And the first three steps are very simple. So if the horizontal derivation has length 0, then moved variant is the same as the given derivation, so the spines are equal, obviously. If the horizontal derivation has length m plus 1, and I'm able to show that the first step preserves the spine, then the rest is obtained by application of the induction hypothesis. So it remains to prove the situation of the diagram 3. And there the induction base is again extremely simple because derivations of length 0 have a spine always a derivation of length 0 on the empty graph. So it is always the same. The interesting case is this induction step here, where you can horizontally you have one step, one rule application. Vertically there's the first application, and then in further ones. In the first step, you can consider the local Church-Rosset properties, and in the rest you have induction hypothesis, so that the spines are equal, but unfortunately this is not enough to prove it. One can see it in this picture. It is the same as before. We have to the left the given derivation D, to the right the moved variant. The last step I call tails of the derivation, and then we know by induction hypothesis that the spines of the tails are equal. So the excess parts of both tails are equal. And above you see the first rule applications with the Church-Rosset property. And I have added all the intermediate graphs here because they are very important in the construction. The Church-Rosset property means that the two rule applications, the matches of the two rule applications, left and right, are equal, have equal matches, and that also the right matches are equal in the intermediate graph of the second application of the horizontal case. So, and then you can move from then you can move from the excess tails here by intersecting them with the intermediate graphs, and the intersection can be proved to keep the identity. Then you have here the excess parts with respect to the tails. You have to add by union the two equal matches, and then because this is the same, the first rule application is obviously the same, and then you get a graph that is larger than the excess, may be larger. It is at least a supergraph, and as the restriction is already equal on the changing parts, the excess is changing the excess part, the rest of the story must be invariant. So it must be equal with respect to the excess part plus the additional parts that come from the first rule applications. Okay, that's a sketch of the proof. The backward case is more or less for free because backward moving is forward moving with respect to the inverted derivation, and this already preserves the spine. I come to concluding remarks. Last year, and this explains a bit why we considered this at all. Last year, we proposed a proving procedure to prove the correctness of reductions between NP problems. And we considered various well-known reductions. You find them quite often in the respective books. And we looked how our proof procedure behaves with respect to all these reductions. And we found out that nearly in all the cases, and even a few more, we have the following basic structure. The source problem is defined by some rules and their derivations. The target problem is defined by some rules, P prime, and certain derivations. And then the reduction is also defined by rule applications, but in most cases, we had to split it in two parts. The first part, P bar 1, and the second part, P bar 2, and in such a way that P and P bar 1 is independent, and P bar 2 and P prime is independent. So we can move the yellow to the middle and back, and we can move the right one to the middle and back, and in the middle something else has to happen. I don't explain the more things. There again is moving involved, but some more. And the problem you don't see here is in NP problems only the true cases are important, because whenever you do not get true, it is false automatically. And so you have to make sure that to make sure if this is a true case, then this has to be a true case too. And there has to be done some arguments, and there we found out that spine is very helpful. The situation of reductions between N3 problems is very similar to many model transformations. You have source models, you have target models, they have their own semantics, and you have some transformation from left to right. And if all the three are modeled by graph transformation, then you always would like to have that the two semantics are nicely related to each other. And I think I'm pretty sure that in nice cases you can apply moving and spine preserving. What about the categorical framework? We use double push out. So the question is obvious, and this is like this. So the moving is already totally categorical, because whenever you have, and you have seen, I have only used the local Church-Rosser theorems, but if you have them, you can move. With respect to the excess part is the following. The definition we have can be interpreted in a category. What you need is an empty subobject. You need subobjects that are closed under intersection by pullbacks and union by certain push-outs. And then you need an EM factorization to define the image of a matching morphism, and then you have it. And the restriction, as we defined it, we use a Ewing condition, so you need something equivalent. This may be the initial push out, or it may be what Robert and Detlef showed us in the morning as an alternative to construct the push out complement. And finally, to get minimal restrictions, each object has to have a finite number of subobjects. At least this is sufficient. Then, obviously, the theory can be stated, but unfortunately, we failed to prove it in the setting. So this is future work. What about further aspects? We consider as operations, conflux, and interchange as basis. And there are similar operations, sequentialization, parallelization, shift, amalgamation, and so on. So one may ask how behaves them with respect to the spine. And then for example, excess part is accompanied with invariant part. On the other hand, restriction is the inverse operation of extension. Left excess and right excess counterpart. So one may wonder whether this helps to get more insight into all the matters here. Thank you very much.
So,
the question, a situation like that. Thoughts, and if you have negative application conditions.
Excuse me.
If you have negative application conditions, do we have local search for this negative application conditions? Do we have principle for simple negative application conditions?
I think that this should be no problem to get moving, even better. So, because then more possibilities are. So if you restrict the rule applications and the restricted rule applications are independent, then the moving is possible even if the general case may not be independent. So this may help to improve our applicability.
So, I mean, just coming back to my question. So, indeed, when you showed in the beginning statement of the problem, is indeed just an instance of trace equivalence. So, when you have a sequence of derivation and another sequence of derivations, and each of them is a trace rate, so it's a minimal derivation sequence. If the synthesized rule, the derivation, which goes from state G0 to Gn, let's say, is sequentially independent, for example, with another sequence, then trace equivalence shows that you can swap the two derivation sequences. And that works for any MRT category, for SSP push-out, for double push-out, for negative application conditions. So I'm just saying that, I mean, the proof is relatively short because you show for each sequence you generate the taste state. You can then swap the basis of the traces and then you just need
but you see that since you get obviously the moving in this way, but how do you get this? The spine is the inner core of the derivation. This is the part of the derivation where something happens.
Yes, but
how do you get this in the general?
So,
and I showed you in the at the end that to define it in a more general setting is not the problem. Our problem was that we had to use the particular role of the intermediate graphs. So in the category of graphs, you can construct the push-out complement as a subgraph of the start graph and the directly derived graph. And this is a property that is not so easily available. I expect that clearly it can be done in a more general setting if you work with sub-objects, as categories with nice sub-objects.
But you need to work in a position.
Yeah, right. So, I expect that everything we did is possible in a more general setting. But I failed to do so.
I'm trying to tell you this. That's the question I know. Think about this trace.
The trace is a derived rule.
It's the entire derivation. So it's a minimal derivation.
If you have
the spine.
You have an n-step derivation, and you take the minimal derived or the minimal production of that n-step.
No, and the data of how the other steps. I mean, it's a minimal n-step sequence from which you can synthesize a one-step derivation, but you also have the data of what you have to what's the spine.
Yeah. The question would be if the spine is the same as a trace net. But I think the trace
one part of the data
is almost whether that's the same concept, maybe expressed in slightly different terms, or whether that's There seems to be some relation, but maybe the data associated with one or the other. Same.
Okay, maybe we should block it. Okay, so I think next is speaker again. I think we continued. Yes.
Adam, can you leave the session open just for a second? I mean, it's not a Zoom session, sorry, the Zoom session open, and use it both in the session open.